Alright, hello everyone. Sorry about the delay in making videos. I'm getting a new microphone system, but it's arriving tomorrow, so I tried to set it up today. I messed around with it for a little bit. Didn't end up working. I posted the video, but didn't have any sound. So that's why that video is not up anymore. And now I'm redoing the video on my laptop. So here it is. Um, let's say we have projectile that we're shooting, right? So maybe we shoot it like this. We have initial velocity vi. We make it at an angle theta. And I want to prove that my gut feeling is at 45 degrees, I'll be able to shoot it the farthest distance, and we'll call that displacement in the x direction, so d sub x. And I want to prove that it's 45 degrees, or I want to kind of know where that 45 comes from and how I know for sure what that 45 degrees is. And I want to make sure that I can't shoot it a little higher. If I go too high, it might not go as far. But if I go too low, it's not going to stay as long in the air. So I think it's going to be 45. I mean it is 45, but I'm just making a scientific prediction here. Anyway, let's go ahead and get started. So here we have our displacement in the x direction, and we know that's going to be equal to our velocity in the x direction, or initial velocity in the x direction times time. That's kind of your basic meters per second times seconds equals meters. Those are the two units of the two things we're working with, so I think that makes a lot of sense. But I don't know either of these things, right? We're not given initial velocity in the x direction, we're just given initial velocity. But I can solve. I can say, well, the initial velocity in the x direction is equal to the initial velocity times the cosine of that angle theta. Right, so now I have this first one, and I need to maybe solve for time. But actually, before I solve for time, I'm going to go ahead and do the y one as well. So I can say the initial velocity in the y direction is equal to the sine of theta. Also pretty easy. Okay, so now I can say that this is equal to this, and I can substitute this equation into there. And now I just need to solve for time. All right, but what is time? Well, time is kind of time in the air, right? And the only thing that time is dependent on is it's dependent on how high we go, right? So if you look at that red arc there, the reason it doesn't go very far, it has a lot of horizontal initial velocity, right? More so than the orange, but the orange is in the air longer, right? And so the orange doesn't have as much horizontal velocity, but it's in the air longer, so it can travel farther. The red has more horizontal velocity, but it's not in the air as long, so it still doesn't travel very far. They actually end up traveling the same if the red line is 30 degrees and the orange line is 60 degrees. The reason they travel the same is because 30 plus 60 adds up to 90, so there are complementary angles there. But we don't need to get into that today. All right, so I want to know what time it's going to take when I hit the ground at some distance d, right? So making a function that works for all angles is kind of what I'm trying to do. And so I can say, all right, final position in the y direction equals the initial position in the y direction. That's actually going to be 0 because we're going to start from the ground, times the initial velocity in the y direction times time plus 1/2 at squared, 1/2 a t squared. And again, this acceleration in the y direction is really going to be acceleration due to gravity, and that's a constant. Okay, so what's yf? Well, y final, so when we launch it up, we go up, 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 up. We hit our peak, and then we come right back down. So y final is going to be, I want this time t here when I hit the ground, right? But the y final, the final height is going to be 0, right? I'm hitting the ground. And the initial position is going to be from the ground, so we'll just leave that. If you want to look at kind of a different way of doing this, you surely can. And I encourage you to try and play around with what if you launch it for different heights, what's the right angle there. But I think that's going to be kind of beyond the scope of this video. So I'm going to go over here and say, take the second equation we did here. So it's the initial velocity in the y direction is equal to the initial velocity times the sine of theta times t plus, moving over, 1/2 the acceleration, I'm just going to write due to gravity, times time squared. I can factor out a t. I can say that's equal to time times the initial velocity times the sine of theta plus 1/2 times the acceleration due to gravity times time. And that's going to be equal to 0. So if we factor this equation, we either have this is equal to 0, so it's we'll call this, A times B, right? So A times B, if A is 0, the whole thing is 0. If B is 0, the whole thing is 0, right? So that's kind of how you factor. If this is the 0 we're looking for, this is the time before we throw it, right? So that makes our initial height 0, which is what we assumed in the beginning, so that's not really important to us. But if we set the second part equal to 0, that's really important to us because that's going to be when the object hits the ground. So we'll go ahead and do that. Set this second part equal to 0, find the second factor. Sine theta plus 1/2 a g times t. We're going to move this side over to the other side of the equation. Okay, so we have 1/2 acceleration due to gravity times time equals the initial velocity times the sine of theta. Now we're going to move kind of this chunk, but not the time, because we're trying to isolate time back over here. So I'm going to go ahead and say, I'm going to multiply this by 2 to get rid of that first, and then I'll divide by this acceleration due to gravity. So time is equal to 2 times the initial velocity times the sine of theta all over the acceleration due to gravity. That is the time. Awesome. Okay. So now we know that this time here is the time we can plug in up there. We know that our initial velocity in the next direction, we know that in terms of the things we're given, which was the initial velocity and theta, and all of our answers are in terms of those two things. Awesome. All right, so now what do we do? Well, I'm going to go ahead and rewrite this equation over here, and we'll go ahead and just start plugging in kind of values and seeing where we can simplify, where we can substitute, and all that. Okay, so displacement in the x direction is equal to the initial velocity in the x direction times time. We know that that is equal to, what did we say? We said it was the initial velocity times the cosine of theta. That was the initial velocity in the x direction. And we know that multiplying by time, we said time, if we look down below, it's, oops, I'm looking at my notes here. If we move this, if we subtract this 1/2 AT to the other side, we're subtracting, so this should be a negative, which means that this should be a negative. You might have caught me. Yeah, I'm catching myself here. All right, so times -2 times the initial velocity. It doesn't actually really matter here, but I'm going to go ahead and make sure I'm writing the right things. Times the sine of theta over the acceleration due to gravity, which is awesome. Now we can combine terms here. So the thing I'm going to be very careful about is I want to know what's changing and what's not changing, right? So the initial velocity isn't really important. It's important in how far it goes, but it's not important in what angle will be at the best. So maybe if we're taking out or measuring our cannon, well, our cannon is going to be firing at the same initial velocity every single time, right? And by the same logic, the acceleration due to gravity is going to be the same every single time. It might be different in different practice problems, but it's not really important in finding what angle will get you the farthest distance. So we can go ahead and we're going to try and put all of our constants on one side and all of our variables on the other. Okay, so we'll go ahead and rearrange this, and I'm actually going to take out the negative sign in this -2 as well, and I'm going to do this for a reason you'll see in a minute, because I want to have 2 sine theta cosine theta, because that's a trigonometry that I know. You don't have to. You can definitely keep the -2. It doesn't actually change the answer, but I'm just going to do this for a second. So we'll make it -1 times the initial velocity squared all over the acceleration due to gravity times 2 sine theta cosine theta. We know that 2 sine theta cosine theta is just sine of 2 theta, which is awesome. So we can just kind of substitute that in there. Okay, so what do we have here? Well, if I were to plot a graph of this, right, and I were to plot maybe your angle over here, and then your distance or displacement in the x direction on this axis, right? Well, if your angle theta is 0 degrees, right, so you have your cannon, and it's 0 degrees off the horizontal, that's 0. Well, you're just firing it straight over. But if we're starting at 0, we're not ever hitting the ground again because we're already at the ground, right? So if we have an angle of theta, our displacement in the x direction is just going to be zero. So that's kind of the zero of this function here. I'm going to write this horizontal or vertically. And if we have maybe pi over 2, right, we're launching it straight up into the air. It'll go up, it'll come back down, and it won't really go much either way in either of the x directions, right? It'll just go straight up and straight back down. So pi over 2, or 90 degrees straight up, is also going to be 0. 0 displacement in the x direction. And somewhere in between, we're going to kind of have this curve that looks like this, right? And I want to know kind of the peak here, up here. If you took calculus, you'll know that that's the derivative. The derivative of the, you can write it as the displacement as a function of theta, so d prime of theta. And when that is equal to 0, or the slope of this line, kind of maybe you have your slopes here as it approaches and as it is 0, so a flat line, then we know that that is your max. That's just kind of some basic calculus. If you don't know calculus, no worries, but just pretend like you know what you're doing maybe, or talk to a buddy. But that is how it works. So I'm going to go ahead and scroll on down, and I'll take the derivative of my function. So if d equals, I guess displacement, equals -1 times the velocity, initial velocity squared over the acceleration due to gravity, times, I'm going to go ahead and write the sine of 2 theta. Well, derivatives, the reason why I grouped all my constants together is the derivative of a constant, like the derivative of 2, or 1, it's 0, right? Because the constant, the derivative of a constant, or the rate of change of a constant, well, constant's not changing, so the change of a constant is 0, not changing, right? So this all actually goes away. That's why I grouped them all together. So we can take the derivative of sine of 2 theta, and we can notice that the derivative prime of sine of 2 theta is actually just going to be 2 cosine of 2 theta. If we set the derivative equal to 0, again, we're looking for that flat line, kind of right, where it reaches its peak here. And we can find what angle we're looking for. So here we have, we can divide both sides by 2. So maybe we divide by 2, it's still 0. We have the cosine of 2 theta equals 0. We take the arc cosine of both sides. So the arc cosine of the cosine of 2 theta leaves us with 2 theta, because those are inverse operations. We have the arc cosine of 0. Well, the arc cosine of 0, what is that asking? Okay, we'll say we have a unit circle. The arc cosine is asking of 0 is asking what angle has a cosine of 0. Well, a cosine is kind of, where is it at on the x-axis? So it starts over here, maybe at 1, ends up over here at -1, and as you go this way, you're kind of approaching this top value here, it ends up being pi over 2, and that has a cosine of 0, right? Because you're approaching 0 on the x-axis. So that's pi over 2. That's that angle right there. So the arc cosine of 0 is pi over 2. Actually, I'm going to go ahead and write pi over 2 as 1/2 times pi. You'll see why in a second. It just makes it a little easier to visualize. 2 theta equals 1/2 pi. I can divide both sides by 2, or as I do, multiply by 1/2. So now we have theta is equal to 1/4 pi, or pi over 4. Pi over 4 is 45 degrees. That is a freaking cool answer. All right. So here's kind of how we did that. We started up here in the top left, and we said, okay, so maybe we're going to go straight up. Well, there's no displacement there. Maybe we go straight over. Again, no displacement there. So we'll kind of find a happy medium. If we know the velocity it's traveling in the x direction, and we know the time that it's taking, we can find the initial velocity, or the initial velocity in the x direction, by saying it's the initial velocity times the cosine of theta. We can find the hang time, or the air time, it's taking by finding the zeros of the equation, or the parabola, when when it's hitting the ground, so when the final y position is 0. So we figured that out and we put it in terms of things that we knew, which were the initial velocity and the angle. When we plug that into the equation, we put all of our constants on one side. We used a trig identity that we knew. You don't have to use a trig identity, it still works both ways. because the cosine, you don't even have to factor out the -2. It works the exact same way. You could use a chain rule if you wanted to. We take the derivative, find when it's to find when the angle gives you the max distance, and then we found that that angle would be pi over 4 or 45 degrees. All right, so I think it's an interesting thing to kind of look at is kind of right here, right? So we have our distance. We have this kind of 2 sine theta cosine theta, right? And if you have pi over 4 and you think about your unit circle, right? Well, sine theta and cosine theta of pi over 4, it's just both root 2 over 2, right? The sine of pi over 4 is root 2 over 2, and the cosine of pi over 4 is root 2 over 2, right? So they're both the exact same. So you're multiplying two things that are both the exact same, right? So 2 times two things that are both the exact same. I think that's kind of a special property that we're looking at here, right? And it's even more kind of apparent if we're looking at the sine of 2 theta, right? Because the sine of 2 times that theta, so 2 times pi over 4 is, two times pi over 4 is pi over 2, and the sine of pi over 2 is just 1, right? So the sine of pi over 2 is 1, which means that this entire side actually cancels out. So our maximum distance, when these two things are equal, when the sine of theta and the cosine of theta are equal, when those two things are equal, then that whole side cancels out, so we're just left with this distance formula. And that's why it's really important that when we have an angle theta, so maybe we're launching, this is y, this is x, y, x, and we have our initial velocity launching this way. This is our initial velocity. We can go ahead and we can componentize. This is how much you're traveling in the x direction, right? This is the initial velocity in the x direction. And then you have, maybe in blue, we have our initial velocity in the y direction, velocity initial y, right? So that's how much it's traveling in the y direction. The reason why it's really important that it's pi over 4 or 45 degrees is because when it's pi over 4 or 45 degrees, these two things are exactly equal, right? That is equal to that, right? So what happens if you're, maybe standing in an elevator and your elevator is moving upwards with, a constant velocity, and you want to throw something at 45 degrees? Is that the farthest you can do it? Well, if you think about the situation, what you're really saying is you're saying, if I throw it at 45 degrees, I still have the same component vectors, but my y velocity, because I'm in an elevator, actually gets a little boost, right? This is the velocity in the y direction due to the elevator, right? So really, these two things are not the same, right? Because this side here is a little bigger than this side here, right? It's bigger by, the velocity of the elevator in the y direction. And so that if that's the case, then these two things, 2 sine theta, cosine theta, that's not going to cancel out. And if it doesn't cancel out, or it's not going to be 1, then you're not going to get the nice kind of cancellation that we do here. That becomes 1, and we're just left with this equation right here. And so that's why it's really important that those two vectors have to be the same, right? Another example is, okay, so say you're on a train, right? So let's say we're on a train and we have a little bit extra x velocity, right? And I still want to launch the projectile the farthest, or maybe I'm on a submarine or a battleship. And I still want to launch the velocity the hardest, but I'm going this way in the x direction a little bit more, right? So what's the angle that I should launch at? It's not 45 degrees, because if it's 45 degrees, the magnitude of these two vectors, here to here and here to here, it's not the same, right? And so those are not the same. So you could actually maybe increase your angle a little bit more so that these two would be the same. So this, you also get plus that vector. Maybe this is a little bigger, so now they are the same. So this distance here is equal to this distance here plus a little bit. And if that's the same, right, if this is the same as this, then you're good, and it will be, the maximum possible distance. And I think it's really important to show students kind of how we arrive at 45 degrees, because it is intuitive until you start looking at, what if things start changing, and what if, velocity start changing. And I think getting a sense of where it all comes from is a really important factor in kind of knowing where those changes happen. So Again, the reason why it's 45 degrees is because the sine of 2 times 45, which is the sine of 90, is 1, which makes that entire side of the displacement function cancel out. So we're just left with -1 times the initial velocity squared divided by the acceleration due to gravity, which is the beauty in 45 degrees. All right, thanks everyone. Thank you for watching. Leave a like if you liked this video. I'm making more videos about physics and probably some more calculus videos. If you want me to make other videos, just comment and ask, and I will do that. My microphone adapter comes tomorrow, which is awesome. So now I can record higher quality audio. Yeah, it's a good time. It's a good time at Shawcademy. So thanks for watching, and I'll